Hi everyone, welcome to our webinar today. I'm Liz Mueller, a marketing manager here at Carus Corporation. Today we have the pleasure of having Dr. Pat Evans with CDM Smith presenting on passive in situ chemical oxidation of 1,4-dioxane and chlorinated VOCs using sustained release cylinders. Just a few housekeeping items before we get started. We have everyone in listen only mode to help cut down on any background noise. But if you think of any questions throughout the presentation, please feel free to go ahead and enter those into the questions section that you see a screenshot here on the right-hand side of the slide. We should have time at the end for questions and answers. If for some reason we don't get time or we don't get to a specific question, we have the capability of seeing your contact information and the question that you asked, so we'll follow up with you directly after the webinar. Also, we are recording today's presentation. So if you would like a copy of that, please get in touch with me, or a PDF of the PowerPoint slides. We'd be happy to share those with you. A couple ways how to find Carus. Our website is www.caruscorporation.com. This is our general sales and marketing email address that comes into our marketing group that we can always direct you to the appropriate person to get your questions answered. Or here is my direct email, which most of you will have from the GoToWebinar confirmation email as well. If you're not following us on our social media platforms, we frequently post on these here, LinkedIn, YouTube, Facebook, and Twitter, where we'll post any sort of upcoming events, whether it be trade shows, trainings, presentations, webinars. We'll also post product content as well as employee highlights, etc. And if you're interested in any of our upcoming webinars, you can go to our caruscorporation.com website, and under our remediation tab, you will find webinars. You'll find upcoming webinars, information on how to register, and you'll also find a tab in which we have pages for our previously hosted webinars as well. And just a quick look at our Carus contact information. So we have for our U.S. sales, Troy Leiser and Tim Colgan. We have Lorenzo Sacchetti, who's in our European office and covers all of our European. And then we have Luis Hernandez, who covers Canada, Mexico, and South America for us. And with that, I would like to take this time to introduce our presenter. Dr. Evans is a principal with CDM Smith in Bellevue, Washington, and has 30 years of research and development experience in the areas of hazardous waste remediation, energy, drinking water treatment, and wastewater treatment. Dr. Evans has been a principal investigator on numerous research projects, including ones funded by the Department of Defense Environmental Security Technology Certification Program, ESTCP, Department of Energy Advanced Research Projects Agency Energy, ARPAE, Water Environment Research Foundation, WERF, and the Water Research Foundation, WRF. He is the recipient of the Water Environment Federation McKee Award and 2 Research Grand Awards and 1 Superior Achievement Award from the American Academy of Environmental Engineers and Scientists. He is the author of over 40 publications and holds 4 patents. He received his BS and PhD degrees in chemical engineering from the University of Michigan and his MS degree in chemical engineering from Rutgers, the State University of New Jersey. He also completed postdoctoral research in environmental microbiology at New York University Medical Center. We welcome Dr. Evans.
Thank you very much, Liz. It's a pleasure to be here. Welcome everyone who's attending and listening. We're going to talk about the Carus slow-release chemical oxidant cylinders for passive long-term treatment of contaminants with a focus on 1,4-dioxane and chlorinated VOCs. This project was funded by the Department of Defense Environmental Security Technology Certification Program, and their focus is to demonstrate and validate innovative technologies for treatment of contaminants and also looking at other areas, munitions, ecological restoration and such. And so we definitely appreciate their funding here. And with this project, we looked at the cost and performance of this technology. And I believe this is one of the first demonstrations of the technology to really look at how well it works for these contaminants and what the cost is. And so before we get started, I wanted to acknowledge the project team. We had Michelle Crimmy with Clarkson University and Pamela Dugan with Carus, who were co-PIs. We had a number of people from CDM Smith. Also Nancy Reese with NAVFAC out in Port Hueneme. She was our DoD liaison. Michael Pound with NAVFAC Southwest. He is the remedial project manager at the site where we did this. And of course, Andrea Leeson, who was the lead at the funding agency. So dioxane was the initial focus of this project. Dioxane is an emerging contaminant. The cancer slope factor has changed, and a number of states are now looking at have regulatory limits in drinking water for these, and the EPA is also considering that. It's often present as a co-contaminant with chlorinated solvents, being used as a solvent stabilizer for 1,1,1-trichloroethane. And there are several approaches to look at dioxane to treat it. Advanced oxidation and pump and treat is one that is often used, but it's expensive. It also is not in accordance with DoD policy, and for site owners who would like to have more of a passive treatment, that doesn't work out so well. Other technologies such as biodegradation, we've looked at this in terms of isolating bacteria as long ago as in the 1990s, and these bacteria are slow growing. There are some more recent advances looking at co-metabolism, but this is still an emerging technology. So slow release oxidant cylinders shown here. Here's one with permanganate in it, and here's one with persulfate, and I'll describe these in a minute here. We know that from our early studies, treatability studies, that permanganate and truly unactivated persulfate are capable of oxidizing dioxane, albeit at slow rates. And these oxidants can also address a number of co-contaminants and also be used in large diameter plumes. So the concept here is, one way we can do this is we can have a number of rows or permeable reactive barriers of these oxidant cylinders, and then the contaminants, the idea in groundwater can pass through these, and then these cylinders can release the oxidant, and that oxidant, as it mixes with the contaminants in the groundwater, can treat that, and downstream then we have treated groundwater. If we take a look at the cylinder, what happens in it in a smaller scale, here's a permanganate filled cylinder. It has about 70 to 80% permanganate in it with a wax binder, and that's represented here by this cross section where the purple is the oxidant and then the white is the wax binder. So this would represent a brand new cylinder. When we first put this cylinder into a well, what we find is that water, shown out here in the black, will go ahead and contact the cylinder and will start dissolving the oxidant, the permanganate or the persulfate, immediately. And that will diffuse then into the groundwater where it can mix with the contaminants. And so this wax matrix is left behind, as shown as the white right here. As we go on in time, we find that more of the oxidant is released into groundwater and it diffuses through the wax matrix here and the tortuosity in this wax matrix. We get a steady state release of the oxidant through the cylinder into the groundwater. And then over time, we see this core of the oxidant decreases in size. And eventually, the oxidant cylinder is spent, and it'll look something like this. We'll still have some remnants of the oxidant present, but mostly it's an inert wax cylinder that can then be removed and replaced. As we'll show you, we anticipate that these cylinders last about 6 to 12 months or so. So now we can use a permeable reactive barrier. We can also use a funnel and gate, as shown as two different depictions right here, where we would have a gate that would be, or a funnel that would be put in, and then we'd have a gate with multiple cylinders in here, and the groundwater will will flow through this. The oxidant will be released from these cylinders in the gate, and then we'll go ahead and treat the contaminants. So the objectives of the demonstration were to demonstrate this slow release chemical oxidant technology for treatment of 1,4-dioxane and chlorinated VOCs. We also wanted to demonstrate that we can use permanganate and we can use persulfate without the addition of an activator such as hydrogen peroxide, ferrous iron, or high pH in order to promote the oxidation of dioxane. And then we also wanted to minimize potential secondary effects that may appear in the groundwater down gradient. So we started off by doing some treatability tests, both in our laboratory in Bellevue, Washington, and in Carus's laboratory. And we had two columns here, one with permanganate cylinder. So this was a small 4-inch long cylinder down here, and then a persulfate cylinder down here. Groundwater flew upward, and this was using soil from Naval Air Station North Island near San Diego, and then also groundwater from that site. You can see here in the pink this is the persulfate or permanganate that's being released. And then what we did is we took a look at the oxidant concentrations and the ability of the oxidants to destroy these different contaminants. This was designed based on a number of batch studies we did where we developed second order rate constants for the permanganate and the persulfate with the different contaminants that we were interested in. So these two graphs show results for permanganate. On the left, we have the concentration of dioxane and permanganate shown with the percent removal. And then over on the right here, we have a graph looking at trichloroethene as a representative chlorinated solvent. What we found here is that our influent concentration of dioxane at the site was quite high, about 10,000 ppb. And then we have our effluent concentration. You can see pretty much the same as the influent. The percent removal over on the right-hand axis was not very good at all. We saw an initial concentration of permanganate up around 1,000, 2,000 ppm that would decrease over time. And so we thought, well, maybe we have too high of a flow rate, too short of a residence time. So we decreased our flow rate right here. We see our permanganate start to increase, but we still see low removal. And this was a bit surprising because we designed this based on the second order rate constants that we developed in batch studies. So that was very disappointing for dioxane removal. On the other hand, looking at TCE and other chlorinated solvents, we found we got complete removal down to detection limits, so greater than 99% removal. These concentrations were removed from about 10,000 ppb down to non-detectable concentrations less than 0.1, so many orders of magnitude of removal of the contaminant. We saw the same thing for other contaminants such as cis-dichloroethene and even some of the chlorinated ethanes as well. So this was the result for permanganate. What about persulfate? Here we use sodium persulfate. Again, we did not use any activator added. We just had the cylinders that were releasing the persulfate. Here we see a very different result. We see our initial dioxane concentration, and initially we saw low effluent dioxane, but then this was increasing as is shown in the red squares. And so at this point we again reduced our flow rate, and at this point we saw our effluent concentrations of dioxane reducing to less than 100 ppb, so 2 orders of magnitude being reduced, and so we're seeing 99% removal of dioxane, which was an excellent result. We see our concentration of persulfate increasing initially from around 1,000 ppm to greater than 10,000 ppm. We take a look at our chlorinated solvent removal. It wasn't as good as with the permanganate, but it still was quite good, greater than 99% removal, and reduction of about 2 orders of magnitude of our TCE. And so based on this, we said, well, why do we have the differences here in the permanganate and the persulfate? We expected, based on our batch studies, that both of these will work. Well, we took a look at our effluent oxidant concentrations, and the persulfate concentrations, we saw this would increase over time, whereas the permanganate decreased, and the permanganate concentrations were quite a bit lower than the persulfate concentrations. And why was this? Well, what we found is that the permanganate, it will be reduced to manganese ion, and it would then deposit as manganese dioxide on the outside. You can see this crust on the outside of the cylinder, and on the inside of the cylinder, there's a lot of unreacted permanganate. And so this crust was then limiting the mass transfer of permanganate out of the cylinder, and this is the result. We had much lower permanganate concentrations in the bulk fluid than what we would expect. With the persulfate is reduced to sulfate. Sulfate doesn't precipitate, and so we did not see that issue here. And this is the reason that Carus now has decided to stop distributing these permanganate-only cylinders, and rather they have the SRS plus cylinders, which have both permanganate and persulfate, and to limit this mass transfer limitation. So, but nevertheless, at the time we did the demonstration, this was a new result, and we found that we had better results with persulfate, so we went to the field with the persulfate cylinders. So this is the site description. This is done at Naval Air Station North Island, out on Coronado Island by San Diego, and we did this at Operable Unit 11. This is down gradient of an impoundment where sludge and other waste from their wastewater treatment plant were deposited. That's since been remediated and with a cap. But still we have remnant concentrations of dioxane and chlorinated solvents going down gradient in this direction here. You can see some typical concentrations of these solvents and the dioxane, quite high. Dioxane are some of the highest concentrations that you'll see at many sites. Often you'll see concentrations of dioxane at sites that are 1 or 2 orders of magnitude lower than this. And so this was kind of an extreme case and a good place to demonstrate this technology. If we take a look at the cross section, what we have is groundwater flowing from right to left here. Groundwater about a thickness of about 15 feet above the silt semi-confining unit. And this is where most of the contaminants were. There were some contaminants down here, but we focused our demonstration in this area here where the greatest mass of the contaminants was and the greatest flux. This was a silty sand aquifer, so relatively homogeneous, good place to demonstrate this technology for a first demonstration. What we did is we had 2 cylinders that were put in, or 2 cylinder boreholes that were put in wells. In each of these, we put 12 cylinders on top of each other into these boreholes. These were 4-inch or 6-inch wells. And then the gradient and the groundwater flow direction at the site is very flat and sort of mounding. And so we said we needed to get good hydraulic control to be able to really do a good demonstration. So we put an extraction well and we extracted groundwater here at a low flow rate, about 0.3 GPM, and then re-injected it down gradient. This is not a requirement for implementation of this technology. Rather, this was to get a consistent and known direction of groundwater flow in order to be able to evaluate the data. So we put in these cylinders, and then we had an up gradient monitoring well, and then we had a series of down gradient monitoring wells as well. In the cross section, you can see how this was done. We had our wells here, our up gradient well. Here was our cylinder well, and then down gradient, our different wells here. all above this silt semi-confining unit. These are some photographs showing the cylinder installation. We customized a system to hold this with stainless steel cable and some stainless steel discs to hold the 12 cylinders on top of each other. And this could be done in a number of different ways. Carus has developed some different cylinder holder technologies. This was something we created on our own. And then this was lifted using a drilling rig. These cylinders are not that heavy. You don't need the drilling rig, but that's what we decided to use in this case. So it goes ahead and lifts the cylinders up here, and then they're lowered into the borehole, and then we put a cap on it. And so it's when the cylinders are spent in about 6 to 12 months, easy to go ahead and pull these out and put a new set of cylinders in. So pretty easy, took about a half a day to do this or so. So the initial approach for this project was to use hydrosleeves in those monitoring wells to sample. We found that the hydrosleeves did not work that well. They weren't very representative of discrete depth intervals. And they weren't capable of sampling the groundwater down near that semi-confining unit. One of the issues also is we weren't sure that we actually had as good of groundwater control as we had planned based on our mod flow modeling. So we modified our plan and we did direct hydropunch sampling at a number of different locations with a new set of cylinders, and to see what the actual flow path was and to be able to do this depth discrete sampling. So here is the modified plan view. Here we can see our cylinders, and then here are the existing monitoring wells. And so then these red crosses are where we did our hydropunch sampling. So we could see we did our main flow path was 295 degrees relative to north. And then we did a number of different transects at different angles to see, well, was the groundwater and the persulfate really flowing this way? Or was it maybe a little bit to the west or a little bit to the east? And then in addition to looking at these different angles, we also were able to look at, well, what is the effectiveness and the transport of the persulfate and the contaminant destruction, different distances down gradient of the cylinders. And so 3 feet down gradient, 8 feet down gradient, and 14 feet down gradient. So the graphs I'm going to show you now represent what we're seeing in terms of these different angles and also in terms of these different distances. Also be presenting the data in terms of feet easting relative to 245 degrees. So how far east along this arc or how far east along this arc. So this is one of those looking at along the actual flow path. And so these are 3 different transects, one at the design transect of 295 degrees, and then one a little bit to the west, 289 degrees, and one 308 degrees a little bit to the east. And so what we see in the sodium persulfate is the greatest concentration of sodium persulfate was actually at 289 degrees, not at the 295 degrees. And if we look at our dioxane destruction, we also find that's consistent with the 289. So our flow path was a little bit west of what we had intended, and this was an important finding. We find our chlorinated VOCs, total VOCs, also we saw that was reduced mostly. Now that's not to say that we didn't see any reduction at 295 and 308. We did see reduction, but it was mainly in this area right here at the 289 degree flow path. If we take a look, these cylinders were spaced about 5 feet apart, and one big question that often comes up is how closely do you need to space these cylinders? Is 5 feet good enough? Can you do 10 feet? Or does it need to be 1 foot? And this is very important because it clearly affects the cost. And if you have them spaced too far apart, then you're going to have groundwater just flowing in between the cylinders and not getting treated. So we need to know what that optimal spacing is to have a cost-effective design. So this graph here is looking at the sodium persulfate in the blue squares, the dioxane in the red or the black triangles, and the total VOCs in the red circles in concentration on this graph, and then percent removal on this graph over here. And what we can see is that the main 289 degrees was right around here. And then 295 degrees was right around here. And this is demonstrated in terms of distance easting from that 245 degrees. We find the main concentrations of persulfate are in this area here, which is about a 10-foot zone of influence or so. We get the greatest reduction of dioxane and VOCs right here at about 11 feet east, and that's corresponding percent removal here, about 90, greater than 90% removal. And so we don't have as great a removal if we go about 10 feet to the east of this. However, keep in mind we only have 2 cylinders in this permeable reactive barrier. 2-cylinder boreholes. If you had a true permeable reactive barrier, you would have multiple cylinders all in a line. So what we believe we had is we had water coming in from the side, cross gradient. And this, we would have seen better results if we did have more cylinders here. And so, but this is a reasonable result for right here. And it seems that a 5-foot spacing is reasonable, but for each site, this needs to be determined. If we take a look along the flow path, we find excellent results. We're seeing that our dioxane and our chlorinated VOCs are being reduced to very low concentrations, from concentrations around 20,000 part per billion down to less than 100 parts per billion. This is 99.0 to 99.3% destruction. Our goal was greater than 90%, so we exceeded our goal by an order of magnitude. So this was a very exciting result. We find that the persulfate, it maxed out at about 8 feet down gradient, so not a long distance down gradient. And even as this persulfate was reducing, which you would expect because it's going to decompose, we saw that the destruction of the contaminants in the flow path was maintained. And this is what we want when we put in a permeable reactive barrier. We want to destroy the contaminants as it goes through the barrier, and then the contaminants stay low concentration. Now, were the contaminants truly destroyed, or were they just diluted? Also, what were the secondary effects? If we take a look at 2 different flow paths, we see that as we go along, we find that the pH would reduce. And this is what we would expect because persulfate will decompose into sulfuric acid. And so we expect that, but the pH did not decrease to an incredibly low number. It was at the lowest around 7, a little bit above 7, so that's not bad. But that's going to depend on the alkalinity of your groundwater. But then the main point though is that as we go down gradient, this pH would rebound. And so we're getting back to conditions that are similar to what we had up gradient. We found that our oxidation reduction potential, that would increase. And then as we go down gradient, it would decrease. And so this is important with respect to mitigating secondary effects. One of the potential secondary effects of any oxidant, whether it's a slow release oxidant or it's a traditional ISCO, is converting trivalent chromium into hexavalent chromium. In the treatability test, we did see formation of hexavalent chromium, but we anticipate that down gradient with anoxic conditions, either by abiotic or by biological processes, this hexavalent chromium would be reduced. And so this is something that you want to pay attention to when you're evaluating this technology. Now, what I've shown you so far have been results in the deep zone near that silt aquitard. What about in the shallow zone? And so this is up near the water table. And here we find that there wasn't much dioxane present. Most of the dioxane was in deep. So we really couldn't evaluate removal of dioxane. But the VOCs were at higher concentrations, not as high as in the deep, only about 5,000 instead of about 20,000. And here we saw a reduction of the CVOCs. Now this was at about 70%, so not the 99% removal we saw, but take a look at the persulfate concentrations. They're on the order of about 100 parts per million, whereas in the deep, we were on the order of about 1,000 parts per million. So this makes sense. If you have a lower concentration of your oxidant, you're going to have less reduction of your contaminants. But why was this concentration of persulfate lower? Why was it lower at the shallow samples compared to the deep samples? Well, we find there was some density-driven flow. If we take a look at the concentration of sodium persulfate on this log scale, and we took a look at our two different flow paths, 295 degrees and 289 degrees, and the red and the yellow in the shallow, and then in the deep, in the green and the blue, 295 degrees and 289 degrees, and then different distances along the flow path, we find that as we go down gradient, there's a greater difference between the deep and the shallow concentrations. Even 3 feet down gradient, we see some differences. But as we get 8 feet down gradient, we're talking a couple of orders of magnitude down difference. And then as we get 14 feet down gradient, we don't detect any of the persulfate in the shallow, and we do still detect about 1,000 parts per million of persulfate in the deep. And so we see this density-driven flow, and this is mainly because we have a very low gradient at this site. And this is based on work that was done by Schillig back in 2014, published in Groundwater Monitoring and Remediation. They did a very nice study, a lab study, to really focus on tracers tests. And it wasn't focused on persulfate or oxidants. It was rather saying, if you put a tracer into groundwater, is it going to give you a good representation of the groundwater velocity, or is that tracer going to sink over time? And that's a very important question. So they had sodium chloride tracer, and they would have different concentrations of that. And then they would say at different horizontal gradients, 10 to the minus 6 to 10 to the minus 2, what was the vertical fraction of the flow? So the idea is that at 0% VF, you have 100% horizontal flow. There is no downward migration, no downward or vertical velocity gradient. At 100% VF, you'd have no horizontal flow whatsoever. The flow gradient or vector would be purely downward. So if we take persulfate, where we were at about 1,000 ppm or so not exactly the same density as sodium chloride, but for this evaluation pretty close, our measured gradient was 4 times 10 to the 4th, which was less than we had planned based on our mod flow modeling. And this could be because of the estimate of the hydraulic conductivity from 20 years ago was not accurate. And so, but this is the gradient that we measured. And we find that at this 1,000 ppm and this gradient, it corresponds to about a 72% vertical fraction. So this is what we would expect based on this data, and this is what we observed. Now, this, if you have a very flat gradient at a site and you're putting these oxidant cylinders in, then you can expect there is going to be some sort of a vertical velocity vector that you have to take into consideration. If you have a higher gradient, then it's going to be less important. It also depends on your groundwater velocity and what the persulfate concentration is. If you have a fixed number of cylinders and you increase the groundwater velocity, you're going to have a lower persulfate concentration, which would change this picture. So this is something that's very important to look at. In our case, we had that silt aquitard, and so it ended up being a good thing in our case. Another question is, well, what's going to happen with the persulfate and the dioxane over time, and how do we model this? How do we determine, how do we design the systems? And if we take a look in our cylinder boreholes, we find that our sodium persulfate measured would decrease over time after, in this case, after about 130, 140 days or so, our persulfate concentration was decreasing over time. And if we take our second order rate constants and we use a model to predict how much the dioxane should be reduced, we get this dashed line. and the squares are the actual observed concentrations. So what this says is we're able to predict how much dioxane we would destroy if we know what our persulfate concentrations are over time, what they are in space, and what our second order rate constants are, which we can easily measure in a laboratory study. The other aspect of it is, well, how long does the cylinder last? And we find here the sodium persulfate would decrease over time. Initially, we thought that the persulfate concentrations would be constant, and then when the cylinders were spent, then we would see a decrease. That wasn't the case. We saw this exponential decrease in persulfate, and after about a year or so, we saw about 8% of the persulfate remaining. And so in this study here, we only went to about a half year, and we know for a half year, there was plenty of persulfate to result in good destruction of dioxane and VOCs, but there still is some persulfate left after about a year. And so at certain sites, depending on your contaminant concentrations, your remediation goals, 1 year, maybe they may last 1 year. But probably not much more than 1 year. So a key part of any ESTCP project is to look at performance objectives and set that up at the beginning in your work plan, or as they call it, the technology demonstration plan, and see if you met or you exceeded those. So these were the performance objectives for this project. Technology effectiveness was destruction of dioxane and chlorinated ethenes, and the goal was 90%, and we exceeded both of these. Interestingly, we also saw destruction of 1,1-DCA, which you would not expect with persulfate. And so there's some activation there going on, even though we didn't add an activator. But we do know that persulfate can self-activate. It just decomposes naturally. And then also there are minerals in the soil. Iron, manganese, these can also promote activation and so this may be why we saw the destruction of the DCA. Sustainability and longevity, we had two different metrics. We initially thought the concentration wouldn't change over time. We found out that wasn't the case, so that wasn't met. However, the more important objective is that we have significant removal, 90% removal for an extended period of time. We stated for 4 weeks, which maybe was a little bit of an easy goal, but we saw we got greater than 90% for 119 days. And so no, we didn't measure it any longer than that, but we expected it would last maybe up to a year in that. So that was exceeded, and so that was a success. Now, if we also take a look at transport and destruction, we want to make sure that we transport the oxidant, but we don't want it to be going so far down gradient that it causes problems at down gradient receptors. And we saw that up gradient, it was about 2100, but down gradient, we were at 21 milligrams per liter. And other data indicated that this was on its way to going down to 0. So this would indicate that these oxidants would be consumed as you would expect. In looking at secondary effects, we know our pH and ORP and persulfate, we saw that met expected trends. We did not measure our dissolved metals in the field study, but in the lab study I mentioned we did see some hexavalent chromium, and we anticipate that that would be reduced. We've seen that in other studies. Another thing to look at is bromate, if you have bromate in the water, but that can also be reduced down gradient. The final aspect of the study was looking at the cost. Is this cost effective compared to advanced oxidation or other technologies? And so we came up, the idea or the intent of this technology was for long-term treatment of plumes. If you want to just go ahead and do a one-time ISCO treatment, it probably makes more sense to go ahead and just inject the oxidants. But if you are looking for long-term treatment where you are going to have either back diffusion of your contaminants or you have a source that you're not going to be able to get rid of, then this is a technology that is well suited for that. So we said, well, let's take a look at a 30-year treatment of a dioxane plume. We also looked at chlorinated VOCs, and these were the conditions for this particular site. And we looked at 4 different scenarios. One was a permeable reactive barrier with these sodium persulfate cylinders, similar to what we did in the demonstration. Another case was a funnel and gate using the oxidant cylinders, so a different form of configuration, which may be more appropriate for some sites. And then we also did a permeable reactive barrier with wells. And the idea was, let's inject the same mass of sodium persulfate, but instead of adding that mass by using the cylinders, let's have a contractor go out there and inject aqueous sodium persulfate. And so this has got the capital cost of buying the cylinders and putting them in there. This, the persulfate itself is less expensive, but you have the labor associated with putting this in more frequently. So how do these two compare? And then finally, how do we compare this to AOP? So here are the results. We have net present value over 30 years. We present both the capital expenditures and the operating expenditures. In this group right here, we have our cylinder permeable reactive barrier where they're replaced every 6 months. This is conservative. They could possibly be removed every 12 months, but we're conservative in this case. And then we had this at different well spacing. This is what we did in the demonstration, 5 feet, but maybe you could go farther, but at maybe some sites you'd have to be closer. In this case here, we're looking at that aqueous injection. And so here we're 5-foot spaced wells. And so compare it to this bar right here, and then different injection frequencies. You can't inject every 6 months here because the groundwater is constantly flowing. And as soon as you inject it, that persulfate is moving down gradient. So you have to continuously come back in and inject at some frequency. And we looked at a range of 30 to 90 days. Then here's the funnel and gate. And then here's the pump and treat. So if we take a look at this, we see, as you would expect, the closer the well spacing, the more expensive. All right, you're going to have greater cost of replacement because you have to be buying these cylinders, and it takes more time to put more cylinders in if they're spaced every 1 foot. And there's a bit more of a capital cost associated with putting in more wells for these cylinders. And so now if we compare that, this one here, to the 5 foot to this here, we find that under all conditions, the present value is more expensive than the 5-foot spacing right here. So this demonstrates that using the slow release cylinder is definitely more cost effective than having a contractor going out and injecting these. If we do the funnel and gate, we find that was a little bit more expensive at this hypothetical site than the permeable reactive barrier. But depending on the sites that you're at, and let's say you have a building over it and you can't put a nice permeable reactive barrier of wells, you may want to go with a funnel and gate. And depending on the conditions, a funnel and gate could be less expensive. So this is all very site specific. And then finally, the pump and treat, it was more expensive than the 5 feet, about $500,000 to $1 million more present value. But again, if you could go with 10-foot spacing, that could be less. So again, for this case, it showed that the cylinder was the most cost-effective approach. So when we scale up, we need to consider a number of different factors. One is, well, what oxidant chemical do we use? Do we use persulfate? Do we use a mixture of persulfate and permanganate? And this, we need to first ask, well, what are the target contaminants? What's the natural oxidant demand? Right? These things are, there's a lot of literature out there that's been on studies, been funded by ESTCP. Also, ITRC has a lot of guidance, and different chemical oxidant vendors can tell you, well, what contaminants and what ones will be destroyed. So that's one of the first questions you need to ask. If you're using persulfate by itself, will it, without the addition of an activator, actually destroy the contaminants at your site? A treatability study is a great way to figure that out. Next question is, well, what's the implementation? Is it a permeable reactive barrier, a funnel and gate? How many cylinders do you need and the spacing? And this is also based on the second order rate constants you get here, your hydraulic parameters for your site, groundwater velocity, depth, and all of these things are going to allow you to calculate these sorts of things. The change out frequency, probably every 6 months to a year. But initially, when you put these cylinders in there, you want to do some monitoring and say, well, what's happening to my oxidant concentrations over time? The hydrogeology I'd mentioned is important. We've talked about density-driven flow. You need a design for easy emplacement and replacement, and then you definitely want to do treatability or pilot testing. One thing that is very important is it may be tempting to say, well, we have a lot of wells out at the site and it's expensive. We've been working on the site for many years. We really need to drill more wells. Why can't we just go ahead and put the cylinders in our existing wells? Well, these existing wells are often monitoring wells, and the idea behind them was monitoring, not remediation. And so this is definitely not recommended. You should not do this. Instead, you need to design a system that is in a PRB or a funnel and gate network that allows you to achieve those remedial design objectives, and to make sure that the cylinders are close enough that you don't have transport of contaminants between the cylinders without treatment. And you also want to make sure that the cylinders are not placed too close together, because that's a waste of money. So want to finish up here some key points. Found out that we were able to use unactivated persulfate to treat these contaminants, 1,4-dioxane and VOCs. We found permanganate. It can be quite effective for chlorinated VOCs. This is nothing new. At this site and with this dioxane wasn't the best choice, but permanganate is definitely a good choice for chlorinated VOCs. We found good longevity, 6 to 12 months and a 5-foot spacing, but this will be very site specific, and it's cost competitive. And so really this technology, we were able to demonstrate it's a very practical and cost-effective approach. And with the guidance that will be available in these reports, this can help you to implement this technology. Provide contact information here. Right now, the reports are under review with the STCP, and I anticipate within a few months they will be available at this website. And so please, and we will be posting this webinar on this website as well. So please visit that frequently, and then you'll be able to download those reports free of charge. And so thank you very much for your time, and be happy to entertain any questions.
Great, thank you, Pat. This was great. I know from a Carus standpoint, we've been very excited to be part of this project, so a big thank you to everyone that was a part of the team as well. Just a reminder to everyone that today's webinar is being recorded. If you would like a copy of the recording or a PDF of the presentation, please let me know. Also, if you think of any questions, go ahead and type those in now. If you think of any after we conclude, please get into touch with me and we can get you those answers either through our expert, Dr. Pamela Dugan here at Carus, or through Pat. And we do have a couple questions coming in. So one, was there any one factor of the technology or approach that won the buy-in from the ESTCP selection team to fund this project?
Yes, I think there was a factor that at that time, dioxane was the new kid on the block, and PFASs hadn't yet emerged. And so ESTCP and the DoD was very much in need for technologies for treatment of DoD. And the innovative aspect that we're able to demonstrate that you could use unactivated persulfate to destroy dioxane. And that was a key discriminator. And then also the combination of that with the slow release platform, they liked very much, because the rates of unactivated persulfate of destruction of contaminants are lower than if you activate it. And so combining this slow kinetics with a slow release platform was very attractive to them, and having a passive approach was very attractive as well.
Okay. Do you have any recommendations of sort of a first pass evaluation of a site to potentially use this technology? Is there a go, no-go point?
Yes, I think one of the go, no-go points is, are the contaminants that you have capable of being oxidized by these oxidants? If it can't be oxidized, then that's definitely a no-go point. So for example, doing PFASs, that would be a no-go. Another aspect of it is, do you have something that you expect is going to be a long-term plume that you need to manage? If you have something that you think you can go in and just do a very fast injection of persulfate or permanganate, and then you'll have no rebound and you'll be done, you probably want to do that. But if you have a long-term plume that you need to manage, then and your oxidants can go ahead and treat this, then this is definitely something you want to look at.
Okay. How do you design for spacing and to make sure the water to be treated will make contact with the cylinders? How do you factor in heterogeneity?
This is the key point. This is very important and something we looked at. Really only a starting point. It would have been nice to do the demonstration, having the cylinders at different spacing, but as you know, with everything, budgets are not limited. You can start by doing some modeling. Right, we did mod flow modeling to look at transport and to see, well, how much dispersion would you get of these? But modeling can only take you so far, and so but definitely you need to do that. And then the next step is to do a pilot test. That's really what you're going to need to do. And like we did it here, we did it with 2 cylinder boreholes. If you want to evaluate different spacings, you could have, say, 4 different cylinder borehole spacings that are, say, 2.5 feet apart, and start off with just the outside borings that are 10 feet apart and see what you get, and then go ahead and add another one in the middle, 5 feet apart, and then if you need to go down to 2.5 feet apart. And so, unfortunately, beyond the modeling and the pilot studies, there really isn't anything available. You can, if you want to take a shortcut, you can use the data from this site and say, well, let's go with 5 feet and put it in and see how it goes, and then say, well, if that we need more, you could always go put borings in between those down the road.
Great. One more question. The case studies shown had relatively high VOC and 1,4-dioxane concentrations. Is the extent of the cylinder treatment affected by the concentrations, i.e. does higher concentrations equal greater removal percentage?
So the destruction of the contaminants is under second order kinetics, all right? So it's related to the concentration of the oxidant and the concentration of the contaminant. So if you have a constant concentration of the oxidant, then it's first order in the contaminant. And so you look at log removals. And so at a certain distance, say 8 feet of transport, you will get, in a certain case, 1 order of magnitude. So it could go from 10,000 down to 1,000, or it could go from 100 down to 10. And so the concentration really doesn't matter in terms of what percentage removal you're going to get, but what is important is what your remedial goal is. So if your remedial goal is, say, 1 ppb and you only have 10 ppb, then you need a lot less oxidant, a lot fewer cylinders, a lot less time and space than if you had 1,000 ppb and had that same remedial goal.
Okay. All right. On an earlier slide, you noted the destruction rate increased when you decreased the flow rate in the bench scale test. What was the flow rate prior to and after?
The flow rate prior to and after, I can't remember the exact numbers, but it was, we reduced it by about 50% or so. And so we doubled that residence time.
Okay. What type of information do you feel would be helpful to obtain in a treatability study?
So there are two things, if we go at the very basic level, that you want to get in a treatability study. First, and you want to do this with site soil and groundwater, and so the first thing you want to get is your natural oxidant demand. And preferably you want to get a second order NOD rate constant rather than just a concentration of demand. And Michelle Crimmy and Bob Segrist did a lot of work on this for CERTIP and ESTCP. They have guidance out on there for that. And that's a good thing to do, a pretty easy thing. And we present in our reports how we did that. So the natural oxidant demand, that is key. The next thing is you want the second order rate constant between your oxidant and your contaminant. And with those two things, you are going to be able to then start on your design in combination with a model.
Okay. Is there any limitations to installing a larger vertical treatment thickness, say 30 to 40 feet? Would the cylinders become too costly compared to other technologies, for example, versus injections?
Short answer is in terms of relative cost to other technologies, I don't think it's going to make that much of a difference because you're going to have to treat the entire treatment thickness with any technology. So if you go ahead and you do pump and treat, well, you have to have a well that's that depth, and you're going to have to pull groundwater from those different depth intervals. So the cylinders themselves, they have a certain weight associated with them. You need to make sure that your apparatus is strong enough to be able to support those cylinders, but they don't always need to be all in one long string that's 40 feet long. You could have one row of cylinders that's from the interval, say 10 to 20 feet, and then another row of cylinders that's 20 to 30, and another row that's 30 to 40. So there's a lot of flexibility in terms of how you implement the technology. And but in terms of the cost, I don't think there's going to be, the depth is going to affect the decisions. But again, whatever depth you're looking at or whatever site, it's important to do this design feasibility study and look at the economics and see how it compares to competing technologies.
Okay. And then there's a question about NOD. So with NOD, it's typically a traditional 48-hour NOD. Do you think that's useful, or would you recommend a different type of NOD analysis?
I think as a shortcut, the 48-hour NOD is somewhat useful. It can tell you in relative terms, is the NOD high or low for a site? But it's not the best thing to use, in my opinion. Using the second order NOD, and so you're getting a rate constant rather than just a concentration. And then you can plug that NOD rate constant into a model and say, well, as my persulfate or permanganate goes along the flow path, how much of that oxidant is going to be consumed by the NOD and how much is going to be left for treating my contaminants. The thing with the 48-hour NOD is it's not just dependent on the oxidant in the soil, it's also dependent on the concentration of the oxidant. If you have 100 ppm of oxidant versus 1,000 ppm of oxidant versus 10,000 ppm of oxidant, you're going to get different numbers for your 48-hour NOD. And so, that is difficult to use when you're dealing with a technology where the oxidant concentrations can change.
Great. All right, it looks like we've gotten to all the questions now. Just a reminder, if you think of anything after we conclude here, get in touch with us. We'd be happy to answer any more questions. And again, we greatly thank you, Dr. Pat Evans. This has been great, and thank you for including Carus on this project.
And thank you very much. Thank you for participating, and thank you to ESTCP, and again, thank you to all for listening. Goodbye.
Thank you. Bye.